In the last video on Feynman diagrams, we learned how we can write the time-ordered endpoint equation functions in terms of diagrams. But these aren't just cartoons. Each part of the diagram corresponds to an expression, which is used to calculate the equation function. Now, to calculate the time-ordered equation functions of interacting fields, we need to use a little something called the Gell-Mann-Low theorem. We focused on the numerator in the last video, and today we'll focus on the denominator. We can again expand the unitary operator in terms of a Taylor series. Using Wick's theorem, we can immediately write out the Feynman diagrams corresponding to the correlation function. For zeroth order, we don't really get anything interesting. We don't have any Feynman diagram since we just have one. But things get a little spicier when we look at first order. For first order, we get this diagram called the bubble diagram. Bubble diagrams are diagrams not connected to any external legs. Now recall that Wick's theorem says that the time-order equation functions is equal to all possible contractions, and we have more than one way to contract this. We have three ways, but these all correspond to the same diagram, since they're at the same point. So we multiply the diagram by a factor of 3, called a combinatorics factor. We can also visualize this by looking at all the possible contractions on the Feynman diagram. Let's draw one vertex. We want to get this diagram over here. Let's start with this mini leg over here. We can contract it to 3 other mini legs. This gives us a factor of 3. There's only one other possibility, so we multiply by 1. We also encounter combinatoric factors in the numerator, but we'll touch on that later. Okay, moving on to second order. We now have 2 vertices. Remember, each carrying that factor of minus I lambda over 4 factorial. We get these Feynman diagrams over here. We also get this one over here. Each of these has a combinatoric factor. We can deduce the combinatorics factor by looking at the different ways we can change the Feynman diagram while still corresponding to the same Feynman diagram. Let's look at this bubble diagram. We can separate it into vertices again. Remember, each of these legs represent the same spacetime point, so we can write it out like this. We can see that there are 4 ways to contract this leg to the other legs here. Then there are 3 ways to contract this leg to the other legs, then 2 ways, then 1 way. So the combinatorics factor is 4 factorial. Now remember how we have the factors of 1/2 in the Taylor series? Well, we have to multiply by that. And then we also have the factor of 1 over 4 factorial that comes with each vertex. Multiplying by those leaves us with these factors right over here. We call the remaining factors symmetry factors. For example, this bubble diagram has a symmetry factor of 2, since we divide by 1/2. Each Feynman diagram will have a symmetry factor. It's actually why we have the coupling constants divided by 4 factorial in the Lagrangian, so a lot of the combinatorics factors that lead to the symmetry factor easily cancel out. Okay, so now we have these bubble diagrams popped out of the way. We still have to deal with the numerator. Don't worry, the same concept will still apply. For simplicity, let's consider 1-to-1 scattering instead of 2-to-2 scattering. You might wonder what is meant by 1-to-1 scattering. How can we have an interaction if there are no particles to interact with? Well, this is where the self-interaction comes to play. It is possible for one particle to decay to 2 particles, so having one particle come out is not a trivial process. And technically it isn't scattering since we don't have multiple particles, but you probably get what I mean. The Feynman diagrams for the theory look like this. We can see that each diagram will also have a combinatorics factor. Let's see the combinatorics factor for this diagram over here. Well, there are 4 ways that x can pair up with point A. Note that we aren't looking at how x can pair up with point y since that corresponds to a different diagram. Now there are 3 ways point y can pair with point A. Remember, we always start with how we compare the external points. And now 1 way the leg can pair with the other leg. So the combinatorics factor is 4 times 3, which is 12. We have to divide it by 4 factorial that comes from the vertex. So the symmetry factor is 2 since we now have a 1/2. Okay, let's work through one more symmetry factor. Let's consider the Saturn diagram. There are 8 ways that x can pair with the internal vertices. Once it pairs with 1, there are 4 ways y can pair with the internal vertices. Then 3 ways point A pairs with point B. Then 2 ways for the other point A. And then 1 way. So the symmetry factor is 6. So now we can update the rules we derived for the phi-4 theory. Each leg corresponds to a propagator, and each vertex corresponds to minus I lambda. We can just ignore the 4 factorial and include it when we divide by the symmetry factor. In this video, we learned how to calculate the symmetry factor of Feynman diagrams, and how to draw bubble diagrams. We also looked at the diagrams for 1-to-1 scattering. In the next video, we'll update the Feynman diagrams once more, when we connect the time-ordered question functions with the S matrix. Thanks for watching, and peace out.